Thank you for the introduction, Gilad. So as Gilad mentioned, we have spent quite a lot of time in the last few years profiling HPC applications. So what I'm going to present to you is to go over a few of the examples. I mean, just one example of the HPC application that we have done recently, which is going to show you. But before that, as this is a snapshot of the HPC studies that we have published in the past. For details, you can actually go into the website, the webpage at the bottom of the PowerPoint slides here. So many of these applications are quite popular. We obviously have tried many of them that actually mentioned by Edison like just an hour ago. So we run them and we profile them, but throughout these years we have collected a good list of all those applications. You can find the information there. And we also have created, the installation guides for all these, for some of the applications that we have run. So it's actually make it easier for people who want to follow the steps. As Gilad mentioned yesterday at the opening talk, that we have quite a lot of systems in the Advisory Council. So many one of those systems we can use for doing application studies. People can request for access and log into the cluster center that we have. It's in the Sunnyvale, California. It's in this area. So a couple of the new clusters that we have is the IBM system, which is on the right. This is one of the things I'm going to show you on the performance slides that actually I'm going to show you later on. And we also have the latest Intel cluster, Broadwell cluster from Dell. I think it's way over there on the left side. It's a 32 node, but it's also equivalent to GPU. So so this is the two clusters that I'll be actually talking about in the subsequent slides for the applications that I work on together with David, actually also here too. So first, I'm going to talk to you just briefly about the steps that that we do to optimize performance, or we try to look into why sometimes performance, the bottlenecks. So there are many different areas. So typically, it can be in the bottleneck or in the CPU area, network or I/O. So and we typically do profiling and just to get a sense of how much time that it would spend approximately percentage-wise on each one of those so that we can actually tune for the better performance. After we do profiling, we understand it better, so we can determine whether or not it actually makes sense to do, changing different hardware configurations or, doing software tuning or doing compiler tuning and things like that. So after we have done that kind of profiling, we will have a really, a much clearer picture about what the application does. So, so these are some of the tools that we have, experience with. So obviously for CPU and accelerators, profiling, we have these tools that we have worked on in the past. So, gprof top and perf top and visual profiler. And then we have I/O profiling tools as well. And for the studies that I'm going to talk about, we will be using an MPI profiler because we realize that majority of the time I should spend on MPI when the application runs at scale. So for our studies actually we're going to talk about next, we'll run up to 32 nodes and up to 1,024 cores. So we would be using an MPI profiler and try to understand the type of communication that takes place. So we will be talking about an application called BSMBench. BSMBench is benchmarked, kind of like an application. BSM stands for Beyond the Standard Model. So BSMBench is a flexible and scalable supercomputer benchmark that it was started. It is a way to measure a computational particle physics. It's a benchmark suite that's actually derived from the Monte Carlo code that's used in a computational particle physics. More information actually can be found at the bottom of the for the reference, but there are actually three main things that the BSMBench actually tried to measure. So it tries to measure the computational, the part that in the particle physics actually is more computational dominant. So you have one part of the kernel actually does that. And then there's also another example that that's given by the BSMBench is actually to compute or to measure the computation or communication, sorry. And then the last one is the one that measures a combination of both. That is labeled as the balanced example. So I'll be doing comparisons and showing performance and profiling on those. So so BSMBench is what we will be using for this particular study. In it, we'll be looking at the MPI library performance and interconnect performance, namely a couple of the most common network interconnect that's used in HPC. I'll be showing the performance among the two and try to distinguish or differentiate between the two. And then I'll be also talking about something different on the due to the different architecture, which we'll be using the IBM Power 8 systems for. The first configuration, as I mentioned, is the Intel cluster. That is based on the latest Broadwell CPU. We have 32 nodes up to 1,024 cores using the both Mellanox EDR InfiniBand and also the Intel OmniPath interconnect for the comparisons. The compilers and other software that we were using actually is shown up here, is listed here. So in here, I'm going to go dive into looking into the profiling first, because the way to understand how much of the time or the spend in an application is best to first profile an application. So in here, we're actually able to see that for the three examples that are actually given by BSMBench, so this is the balanced workload, a more computational intensive workload, and also communication. So all three, even though for the computation one, also exhibit a lot of communications. And the type of communication actually takes place among all three are pretty much the same. There are a lot of them actually dominated by the MPI barrier call, which is synchronization call, and also the reduction call in MPI. It's called MPI reduce. So quite a lot of the time actually spent on MPI barrier and all reduce, as we find out. So, and then we will also look into the type of the messages actually being sent across the node for the barrier and also all reduce. The IPM profiler, which I mentioned earlier, is actually used on this study to show the results. So we saw that the 8 bytes and 0 bytes barrier actually being used the most. Similar information is actually shown up here. It's just that they have a different way of showing the result for profiling across all three. So we see that barrier actually takes the most time. So as I mentioned to you, we want to be able to distinguish something is good scaling or not. The best way to do is to compare against something else. So in this study, I actually have a chance to compare different type of network interconnect, such as the EDR InfiniBand right here, and showing up with the Intel OmniPath interconnect here. So what we're actually showing, and what I found is that scalability of OmniPath is actually good until up to 8 nodes, which is around like 256 cores. And we start to see some differentiation, starting with 16 nodes, that EDR is actually able to perform better. And the differences actually will grow at the 32 node and 1,000 cores level. So both interconnect have different type of architectures. So namely, OmniPath is the on-load architecture, and InfiniBand is the off-load architecture, which is one of the difference. And EDR InfiniBand, actually, we're using here, we're actually using the MPI that supports the collective offload, which may actually show additional benefits of for EDR InfiniBand. Whoops, I think I made a mistake here. Okay. The offloads is actually coming out from the MPI library that's called HPCAC, which is what I'm going to show you here. So by comparing Intel MPI and HPCAC, we already see that there's a slight difference. The rest of the difference that I saw in the previous slide, which is up to 20%, is mainly probably due to the underlying architecture rather than the collectives. But inherently, the two MPIs are very different. So OpenMPI obviously is on its own, and Intel MPI is based on the M-pitch variant. So the way that they handle a lot of communications and things like that would be very different. So it's not really easy for me to distinguish like that, though. But I can just show you the difference in performance is like that. HPCAC definitely, that's based on OpenMPI, can scale a little better than Intel MPI. But overall, the hardware-wise, we see that InfiniBand actually performed a little bit better, up to 20%. Second configuration I'm showing you, as I mentioned earlier, is the IBM systems that we recently were able to get our hands on. So the types of IBM servers that are available for us is the Power 8 server. That's not the one that allow us to do NVLink with GPU. So this is the Firestone servers. So, but this is the type of servers that we are able to get our hands on. And we actually want to see and differentiate the performance that we get from the IBM system on this cluster versus the performance on the same application trying to be using the similar tool chains and see if we can get some differentiation and see which one is better. So we will be using same OS, same driver stack for InfiniBand, but obviously the architecture is different for IBM. Is PowerPC, PPC 64 little Indian LE. So there are quite a lot of underlying differences among them. So I'm just showing you the configuration here so that we can compare. Something different about IBM server is that it supports something called hardware thread, or they call it SMT. That stands for simultaneous multi-threading. So the default option that I was using was the number one, which is no hyperthreading enable, or simultaneous multi-threading enable. So IBM actually does support up to 8 SMT threads. They're called hardware threads. So it allows you to do additional threads, and hopefully they actually give you better performance. And we actually were able to see, for the 4 nodes that we have tried, we're able to see slightly better performance across, even on a single node basis, obviously. So slight increase, by using SMT 2 and 4. 4 appear to be a little bit better. So each one of those threads will actually appear as kind of like a CPU core on the when you do like a CAD-prox CPU stack. So you literally can end up with 160 hardware cores on a node. So when SMT 8 is actually set. So another comparisons I've tried is also to try different MPIs that's available on the Power 8 systems. So far we have like OpenMPI, and IBM obviously supports and have available their own MPI that's called Spectrum MPI. That is a new version of MPI that's coming out from IBM. So Spectrum MPI is like an extension to what they have done in the past that's for platform. So platform basically becomes like Spectrum right here. And what's so special about Spectrum MPI is that there are more than 2 actually communication transports available. So one is called PAMI, which is the Parallel Active Messaging Interface, PAMI. And it also supports something called MXM that's available by Mellanox for doing communication messaging. So we were able to see that platform MPI together with MXM are able to show better performance. But the one thing to note is that what we're actually showing you in this platform run is actually we use the Excel compiler that is come together with the support of Spectrum MPI. For OpenMPI, we use GCC, so which may actually explain some of the difference here. We weren't able to distinguish that, though. People come and ask me sometimes what would be the performance difference with the same workload with different architecture. So here I'm taking the best numbers that I got from the Intel side on a single node, 2 nodes, and 4 nodes over InfiniBand versus the IBM system, single node, 2 node, and 4 nodes at its best. So this is the delta that we were seeing. So IBM actually is able to show better, up to 23% or so, compared to Intel. So which is what we will see. And the really strange thing is that even with more cores on the Intel side, up to 32 nodes that we have per node on the Intel side, Broadwell, and 16 actual hardware core that we have on the IBM system, we're able to see, Intel is actually, we're able to see that IBM has actually shown better performance. Right, so this is something that was really interesting because given that IBM has less hardware cores than Intel has, but able to see a better performance over there. So I think I need to wrap up soon, so my allowed time is over. So just give you the summary of what I've just talked about the performance profiling. So here is at the bottom of this page, and some of the things we talked about the results. Thank you very much for your time. Questions?
Working. I was curious why when you're testing 8 threads per core, it was slower than 4 threads per core, and would that be something that you could fix by changing the software? I
found this is something IBM also have found as well on other applications, but somehow, if with more hardware threads, is the either memory bandwidth or utilization of the memory bandwidth is not able to accommodate for 8 threads for some reason. Sometimes even 2 threads and 4 threads will be a limit too. So you cannot you don't get additional benefits by using more threads. This is a little strange, but this is what I have found also on other applications that working with IBM on it too.
So what I'm wondering is if you changed how the software was doing blocking or something like that, would that change it so that now 8 threads per core is faster than 4 threads per core?
I do not know, but I noticed, as I mentioned, that pretty much the applications I was able to look at, either given by IBM or something that I have tried, 8 threads or 8 threads, SMT threads would not show me the best. Somehow there was some limitation. I'm guessing it is more like the memory, bandwidth due to the additional cores. So because you have additional cores and they all needed to have the bandwidth to the cache or to the memory. This is my assumption. But yeah, we have tried, or at least I have looked at other applications too, and this is what I also found, which is why I was, for the applications like this, it always makes sense to try different thread level and see if we can get better performance for the IBM systems. Yeah. Yes.
So BSM benchmark for keeping, right?
Yeah.
Then you showed a 23% improvement from IBM compared to the Intel.
23, something like that. I think 23.
So I think I noticed is this normalized in the sense that the processors feel maybe power is higher than Intel?
It is certainly a possibility. Obviously, IBM systems have run the high clock speed. I'm actually not showing you the slide here, but I believe I also have tried different clock speed. There are a couple of servers that I have for IBM. It's actually made by another OEM that has a higher clock speed. If I remember correctly, I actually do not show, maybe actually not showing you here. Anyway, I'm not able to see much difference even with the different clock speeds for the IBM one. So the IBM one actually comes with different clock speed, and I was able to compare on a single node basis between the two, and that's not the reason. So something else, I think, in the architecture is affecting it. Although I'm not sure, I'm supposed to be showing you that one too, but yeah, yes.
When
Like you,
see what's the difference between the clock frequency, but
right.
bandwidth able to do.
So the bandwidth, meaning the memory bandwidth?
Memory bandwidth.
Yeah, that's the, yeah, right. Usually we try with stream, but I just don't have it in front of me. Yeah, the network bandwidth is the same, obviously, because of the network adapters that we have. Stream, if I remember correctly, IBM always boasts about their memory bandwidth is much better for IOPS and for storage. So, you know, this is one possibility. Another one is probably just because the compiler is actually tuned better for the IBM system than Intel.
I don't know the benchmarking detail, but what could be happening is that
Sorry.
what could be happening is that at certain point you might be hitting a bandwidth wall on Intel side probably and hitting a bandwidth wall, and that's why the Intel performance is
No, it could
lower.
be.
It's just a hypothesis.
No, it could be because there are a lot more cores available, so each one of them do need to have sufficient memory bandwidth. So I think it could be. What could be also be interesting is to reduce the amount of cores on the Intel side and see if we can get better performance, which we typically do. For 32 processes per node, we always reduce to, I know we're out of time, but yeah, 28 and 30, I mean 28 and 24 and things like that. So not always more cores are faster. Yeah. All right, thank you.